All right, everybody, I think I'm gonna go ahead and get started. Gosh, I have 15 minutes between classes and I can never hardly get ready. But here I am and I'm gonna try to get started. I hope you guys are all doing okay today. I've been walking around with watery eyes. I don't know, the air is dry. It was so windy and dusty yesterday and hot. And so if I look like I'm crying, I promise I'm not really too emotional. I'm just dealing with the conditions, I guess, of the air that we're dealing with right now. But anyway, I hope things are going well. Thanks for pushing forward with that homework that you got turned in already on Tuesday. I graded it yesterday and they were really quite good overall, the assignments. So obviously you guys made that happen with just a half of a week to get it done. The next homework will be due on Tuesday. This next assignment is a little longer. And so be sure to get going on it on the earlier side. I'm actually going to probably have well, of course I have office hours today after class. I'm probably also going to have some extra hours tomorrow because my other class has some stuff I need to help them with. So I'll probably open that up to everybody in case you want to talk. Normally on Fridays, I don't always have office hours. But yeah, next Tuesday, we'll do that. I also found out that they're going to do an evacuation drill on this campus next Tuesday, right after this class. So I'll probably be having my office hours out by the fountain. We'll come out and hang out in the fresh air, at least for the first 30 minutes or whatever, until they let us come back inside. But that's not until next Tuesday. So that next homework is due on Tuesday. On Thursday of next week, we will take a quiz. So let me just remind you about that. So that's a week from right now. We're going to take a quiz. So quiz number 2. This will be on Thursday, whatever day that is, November 14th, I think. And it's going to cover chapters 7 and 11. Just the stuff that we've covered. And if you want to break it down according to homeworks, it would be homeworks 6 through 10. These are all of the homeworks that we've done since the first midterm. And number 10 is the one you're currently working on for Tuesday. I'm planning over the next couple of days to get a resources folder together for the second midterm. The second midterm, by the way, is 2 weeks from today. So I'm going to try to get a resources folder put together for you in case you want to use that as a jump start to studying even for the quiz. I think that should be possible as long as I keep up with my promise on that. So I'll do my best to have that ready to go. Sometime over the weekend, you might notice that I have that up and ready for you. So yeah, so between now and next Thursday, you've got a homework assignment to work on and a quiz to study for. That quiz will be at the beginning of class. It'll just be one sheet of paper, probably front and back of one sheet of paper, and it counts the same as a homework assignment, just like before. So it's not that big of a deal, but it just gives you an excuse to sort of start studying a little early for the exam. My plan is to grade those quizzes really quickly and get them back to you. And then that following weekend, on the 15th and or 16th, I'm planning to do some review sessions for the midterm itself. So that's kind of the schedule here over the next week or so. Anybody have any logistical questions so far? Yeah, isn't it great? We have a holiday on Monday. The Veterans Day is coming up on Monday. Does us so much good for this class, doesn't it? I'm just gonna go to the beach for 3 days. And, when you teach Tuesday, Thursday classes, you just don't get the holidays as much. But I think I told you, didn't I, though, last time that we're gonna miss a class, not next week, but the week after next week. So I'll remind you about that later on. So guys, what I want to do here is finish up talking about trees today, and which is really kind of the last thing in chapter 11 that I'm going to be getting into. So we may, depending on how the timing goes, we may get a chance to jump to the next topic as well, which is going to be to discuss planar graphs in more detail. So, which will be the last topic for the midterm. So we're going to be done with the subject matter for the exam pretty early, I think, which should be nice. What I've done here, as usual, is kind of put a summary about what we were talking about Thursday or on Tuesday, back on the board again. Just as a overriding assumption, I'm going to assume that my graph G has order n, so that means n vertices. and that it's connected, okay? So that's actually going to be required in the context of talking about trees. Okay, so what I've done here is I've kind of said, look, how can I tell if a graph is a tree? And I've given you 4 ways to think about it here that are all coming out of our book. The first one is just the definition. It's kind of where the conversation starts, which is just that every edge should be a bridge. If you need a refresher about that, a bridge is just an edge whose removal disconnects the graph. So what we're saying, if we have a tree and we take which is connected to begin with, right? It has to be. It's part of the definition. But if we remove any edge from a tree, then we no longer have a connected graph. Okay, so every edge is absolutely vital. In other words, if you remove an edge, then suddenly you won't be able to walk from any vertex to any other vertex. You might still be able to walk some stretch of vertices in the graph, but you wouldn't be able to walk anywhere that you wanted in the graph. So that's every edge is a bridge, vital to the connectedness of the graph. Okay, but then we have other ways of thinking about it. And we went through the first one here already on Tuesday. A connected graph of order n will be a tree if it has exactly n-1 edges. It's like as few edges as you could have and have the graph be connected. If you had any less edges than that, the graph would be forced to be disconnected. And if you had any more edges than that, then your graph would have cycles in it. You'd have edges you could remove without disconnecting the graph. So it wouldn't be a tree in that case. So G has to have exactly n-1 edges for it to be a tree. Equivalent to that, these last 2 I did not prove yet, but we're going to do that today. The theorem 11.5.4, a tree is just a graph that has no cycles in it. Real easy to remember that and to say that. So it's a connected graph with no cycles. And lastly, it's also characterized by this condition down here, which is a little bit wordy, but it's not anything terribly difficult to understand the concept of it. It just says that between any pair of vertices in the graph, you can find a unique path between them. The fact that there is a path at all is going to result from the fact that G is connected. But the uniqueness of that path is really coming from the condition that you have a tree. So for a tree, there should be only one way to go from point A to point B. No cycles kind of lines up with that as well. Yeah, Kristen.
So on like a test that we want to refer to this, are we gonna have to say like G is a tree, so by theorem 11.5.2 we know this, or on the test can we just say since G is a tree, we know this?
So great question. And I'll just to remind you guys again, I hope I've said this before, I never expect anybody to have numbers of the theorems memorized. I'm putting them here in the notes so that you can go back later on your own and get the book out and refer to them. You can just say, buy a theorem, and that'll be good enough for me, or buy something from the book. It doesn't need to be referenced specifically. Nikolai?
11.5.5.
Yeah.
They almost seem like the same thing, but the fact that it's unique, wouldn't that mean that it's basically a bridge if they're, or if they?
Well, this is a unique path, so that's not just talking about one edge. That's like a whole sequence of edges that are taking me from one point to another. So you have a whole walk basically that you're doing through that graph. So in that sense, I mean, when you say they seem the same to you, I guess I could say, well, they are equivalent. So they should be logically equivalent to each other, but I don't see them as being the same statement. This is just saying if I remove an edge, the graph becomes disconnected. And that's referring to one edge only, whereas this is talking about an entire sequence of edges going from X to Y. Yeah, so, but yeah, if you see them the same, I couldn't really argue against you on that because they are, after all, equivalent. Yeah. Before we prove the rest of the statements here, I thought maybe as a warm-up, we could practice on, I think in the homework, I'm going to ask you to do the isomorphism types of trees of order 7. So I thought maybe to warm up, we could do trees of smaller order, 3, 4, 5, and 6. Let's see if we can do this. Maybe I'll kick things off here. Let's just go in order. I'll start with the graphs of order 3. So this means I'm gonna have 3 vertices, and I can arrange them however I want. I might as well just put them like so. And they want us to draw various trees that we could make with that many vertices. And so how could we do it?
Just connect two of the edges.
Yeah, the first thing is to realize how many edges you're gonna have, right? If n is 3, then of course you have to have 2 edges. So, all right, I'll just draw any edge without loss of generality. I can do that. And then I have to draw one more edge. Okay, well, I can just do that. That's really the only way to do it. You are not allowed to do a multigraph here. It's not talking about multigraphs, it's just talking about graphs. So something like, or even if I did that, well, that wouldn't work. It's not connected. So you can't do multiple edges. This is really the only thing you could do. Up to isomorphism, right? That's the only thing you could do. Yeah, Christian?
Is it safe to assume that we don't say a graph is a multi-graph? It's basically only assume it's one if it's said.
It has to say it. And same thing with general graph. If it doesn't say general graph, then I shouldn't see any loops on your, if you're talking about just a graph or a multi-graph, those graphs don't have loops in them. Good point. Okay, so that's it for order 3. Okay, so let's go on to order 4. And so that means we're going to draw 4 dots. I'll kind of position them as a square here. And I'm going to try and make this a little more interactive than I maybe sometimes do. Is there anybody who would like to come up and maybe draw a tree on those axes? Austin, there you go. And all of you playing out there in the peanut gallery can just check your answers here with what we have. Okay, that looks pretty good. Thank you. That looks great. It's connected. There's 3 edges. That pretty much guarantees it's going to be a tree. Okay. Are there any other isomorphism types for trees of order 4? Nikolai, do you want to come up? See if there's another way to do it that's not isomorphic to the first one. So that's going to be the challenge of it here. Let's see what we can do. Okay, I like it. That was a long walk just for that.
Yeah.
There you go. It's worth it, right? So yeah, so I'll just draw that a little darker here. This is another example of a tree. There's exactly 3 edges and it's connected. There's no cycles in it and so on. Would there be any other way to do it? You have one? Do you want to come do it? You seen it? Give everybody a little exercise today while we're at it. Okay, thank you. Let's see, what do we have here? This graph, what do you guys think? Christian, you're nodding your head no. Caden? So this one, if we sort of untangled it a little bit, right? Do you see if we kind of untangle this one, we can actually make it kind of look like this one. Like if we twisted this vertex up here and this vertex down here, it would actually be equivalent to it. So this one is actually isomorphic to this one, although it doesn't look the same initially. So if we're only doing isomorphism types, we wouldn't draw it a second time. Does anybody else think that they found a different one of order 4? Okay, I don't think so. I think this is it. I think this is actually it. Okay, and these are not isomorphic to each other, even just looking at the degree sequence. Right. So that's an easy thing. Okay, let's go to order 5. And I might draw a couple of them here. I'm trying to remember how many there are. As with everything else, that there gets to be more and more of them as you increase the order of the graph. Later. There we go. I think there should be about 3 of them or so. Do I have a volunteer to come up and draw one? Go ahead, Maddie. do one, and were you raising your hand too? Why don't I give you a marker also, and unless you're doing the same one she is, then we'll have two of them done at least. So. Okay, looks good. So Maddie has drawn the one that basically is just a line of length 4, and then there's sort of an opposite extreme, right? Very good, Julie. That's a vertex of degree 4, and then a bunch of vertices of degree 1 are called pendant vertices. So there's 4 vertices of degree 1 here. Here we have only 2 vertices of degree 1. So those are different. Does anybody think they can draw the third one? Luke, you want to come on up? Right here. Thank you. Sorry. I'm not gonna make a very good quarterback. Yeah, but I can't toss markers. Okay, thank you so much. Let's take a look here. That looks pretty good. There's no cycles in it. Notice that all of these graphs have exactly 4 edges. Right, exactly 4 edges, and this time we have a different degree sequence than either of these two. Okay. So yeah, those look good to me. I'm pretty sure that's the only ones, unless anybody thinks they might have found another one. Maybe not. Okay, let's go to order 6, which is the last one. See if we can draw the trees of order 6, and there will be a few of these as well to keep track of. So for order 6, I actually came up with about 6 of them. So I'm going to go ahead and draw out 6 sort of hexagons here, and then we'll see. You guys can start trying to draw them while I'm setting up here, and then I'm going to take some volunteers again. So 1, 2, 3, 4, 5. I think there's going to be a 6th one here. Okay, so I've kind of given myself room to put 6 trees of order 6 on that board. So I would love to have about 6 volunteers to come up and draw these. And, so if you think you have one, especially if you haven't had a chance to do one yet, I would love to get a volunteer. And don't worry if somebody else is going to draw the same one that you do. We'll figure that out once we've got them up there. Has anybody got one to draw, Christian? You ready to catch it? You got one, Kasha? And Fernando, anybody else? Maria, go. Anybody else want to try? We'll find out in a minute. Watch, they'll all draw the same one.
Given an order.
I looked for that. I just.
I got the names on.
What's that? I don't know if you asked me that before, but it would be a very nice question. How many isomorphs and types of trees are there? Yeah, it's like here we have 1 of order 3, 2 of order 4, 3 of order 5, but then it jumps up to 6. So it becomes a lot bigger. So, did I not pass out 6? I didn't get 6 volunteers yet. You want to try one, Teresa? Eduardo? We're just gonna have a little fun with this. Yeah, you bet.
I'm trying to.
Yeah.
Quick question.
Okay.
Second, but will that be?
Second to the last one is yeah, I think so. We'll fix it in a minute. So, see, the beauty of this is that, since you didn't know what each other was doing, this one right here is the same as the first one. And that's fine, because you're not watching all the graphs, because this is really just one big long line, one big chain of vertices here. And so is that one. So is it okay if I don't know,
Yeah.
this one, was that yours? Okay, that's okay. It wasn't wrong. It's just that everybody's great minds think alike, right? Okay, so what do we have so far? This looks pretty good. This is certainly not the same as this. All of these should have 5 edges, right? This one, 1, 2, 3, 4, 5 edges, and I don't have the same degree sequence as either of these two. How about this one right here? This is also different. Notice I have a vertex of degree 4 right here. It's the only one. It's the only one of these graphs that has a vertex of degree 4. Okay, so I need some more help though. I think those are 4 good ones. Let's figure out what are we missing. And if anybody thinks they know, I can pass out. I got the markers here. Want to try? It's okay if you're not right. It's okay. Yeah, yes, let's give it a try.
Is it, has to do with the degree of like. each
The degree sequences can help you, right? So you would expect,
Yeah, two. I was thinking it's one, and then we have one of
uh-huh,
4, and we have 3.
let's
right?
see. Yeah. Ooh, I like that, Kevin. I think that looks really good to me. That looks really good. Yeah, while start writing the degree sequence. This one, by the way, the handshaking theorem, the sum of the degrees should be twice the number of edges. We know we have to have 5 edges in a graph of order 6. So if we double that, it's 10. So the degree sequences should add up to 10, right? This one is 5, 1, 1, 1, 1, 1. Okay. This one is 3, 2, 2, 1, 1, 1. Are you feeling confident with that one?
I think that was another 2.
This might be what Kevin wrote down. Let's check this. So this is 3 and 3, and then 1, 1, 1, 1. Do you have another idea? Yeah, I think this one is gonna be the same as this one. Because I could take this part and flip it around. So let's try this one more time.
Oh.
You think you have it? Okay, let you try it again. We'll get this eventually here. Well, that one is actually the same as this. You have the hardest job because there's only one more that would work. Let me just see, this one here is 4, 2, 1, 1, 1, 1. So now I'm gonna cheat and look at my sheet because I did these ahead of time. I actually think that the one that we're missing has the same degree sequence as this one. So you can have the same degree sequence and the graphs might still not be isomorphic. Remember that, right? That's only one property. So let's just try. I'm gonna try one more time here. See, unless somebody else wants to try. Do you have an idea how to do it? Okay, why don't you come on up? We'll come on up and grab a blue marker. Let's see if we can fill in the rest of this. This is fun. I love graph theory. So we need it'll be interesting to see what is the structural property that we can use to show that they're not isomorphic to each other. Because they have the same degree sequence, which means they're gonna have a lot of things in common. No, I was just telling Nikolai, there's no simple formula for it. Yeah, okay, guys, let's see what we got here. Does that look like that's gonna have a better chance?
Yeah.
I sure think so. But basically what this graph is doing is it's taking like, see how, like, if we think of this as like the head or the central vertex of this graph, it has 2 paths of length 2 going out from that central vertex. So what Maddie has done is she's taken that central vertex and actually, I think it is the same, isn't it?
Yeah.
Yeah, because this is, you have a length 1 and then 2 and then 2. This is 2, 1, and 2. So I actually think again, it's the same degree sequence. Does anybody think they have?
It'd be easier to see it if you just come up as like. To see it.
You know, we are certainly free to do that. So exactly. So this one kind of is like a line with 2 arms off on the side, except it's upside down. So let me just see. The other one that I have is, let me try Nikolai's idea. 3, 4, 5, 6. So I think the thing that we need to do here is take a vertex here. Well, actually, you know what? I think I'm gonna put it in the hexagon. You can do it either way, but just so we can compare them easier. I think it will be more obvious. So what I came up with, guys, is it would go kind of around here. And then add one more edge there. So this is 3, 2, 2, 1, and 1. So now, see, I don't have any arms of length 2. I have this is 3, 2, 2, 1, 1, 1. What do we have here? 3, 2, 2, 1, 1, 1. Can somebody tell me why these two graphs are not isomorphic?
You can't find a theta.
I can't find, so Amber's in the Zoom. You cannot find a isomorphism theta. That's true, but that's not, like, I can't be convinced of that. Okay, so very, very good. So the two graphs here, they do have the same degree sequence. They do have the same degree sequence, but they're not isomorphic because on this graph, the vertices of degree 2 are not adjacent to each other. Whereas on this graph, the two vertices of degree 2 are adjacent to each other. So that is actually a difference between them. It's a little bit subtle, but that is actually the case. Okay, so I think in the homework, they're gonna ask you to do trees of order 7. Trying to remember how many there are. Try to do it without looking it up on the internet. I think there's like 11 of them. I think that's, yeah. Try to do it without the internet. You obviously could Google this problem and then just look at all the graphs. I'm sure they'll all be there. But try it for yourself and then check your answers like what we did here. Okay, is that you guys understanding this a little bit? I do like Nikolai's point about, you don't have to put these points around a hexagon or an n-gon. You can put them in a line as well. Draw it that way. Sometimes you'll see people preferring to do that too. There's really no right or wrong answer for that. Okay, great. So that's a nice warm up. Gives us a chance to see what some of these trees look like. I'd like to come back and prove the remaining parts of this recap that we didn't have time to actually prove last Tuesday, but which we have stated on the board here. So I've already taken care of obviously the definition and this first theorem, 11.5.2, we did that one on Tuesday, but let's do the proof of theorem 11.5.4, which is the third one in the list here, that G should contain no cycles. So if G is a tree, then it should contain no cycles. So let me get my right page of notes here. In order to prove this, I'm actually going to start with a little lemma first. So within this proof, I'm going to state a lemma, and I will then have to prove the lemma as well. So let me state this lemma. This is actually a lemma 11.5.3. So lemma just means it's going to help us prove the main result of whatever the proof is we're doing. So here's what the lemma says. Let G be a connected graph. Let G be a connected graph, and alpha is an edge of that graph. So alpha is just going to be my notation for an edge, so it's an element of the edge set. Then I would like to have a nice way to identify bridges, or to identify these are edges that when we remove them, it disconnects the graph. So alpha is a bridge. If and only if, this is a way of expressing what a bridge would have to be. Namely, alpha is not part of a cycle. It's not an edge that's within any cycle at all. And you see how that might be related to then proving the theorem that we're going to be proving. Let me start with the proof of the lemma, and then we'll go back to the main result. So proof of lemma, and this is, This is very short. You could almost argue that this is clear. The lemma is clear, but I will write something down. I'm going to prove both directions in contrapositive format. So let me start with the forward direction here, but I'm going to do it in contrapositive style. Meaning that if I assume that alpha is part of a cycle, I'm going to prove that it would not be a bridge, right? So let's just see what we can say here. If alpha is part of a cycle, right? If alpha is part of a cycle, then its removal. So if you remove it, you can still walk between those vertices by just going around the cycle the other way. You are not disconnecting the graph. Then its removal does not disconnect the graph. Since if let's just imagine that alpha was the edge going between X and Y. Right, so if alpha goes between X and Y, we can still take a path from X to Y without using alpha. That's kind of a wordy thing, but just I'll draw a picture here. The picture really isn't part of the proof, but I'll just imagine here that I have a cycle. If alpha is right here as part of a cycle and it connects the vertices X and Y, then you can see that if you removed it, you can still walk from X to Y, which means that you can still walk anywhere that you could have walked before. And because if there was some point in a walk that you were doing earlier that you had to go from X to Y, well, there's a way to get there by just going around the long way around the remaining edges of that cycle. Pretty clear, okay? So that's the first part, and so this means thus alpha is not a bridge. Right. Alpha is not going to be a bridge in that case then. Seems pretty reasonable. Is that all clear to everybody? Yeah, Christian?
Like a way to think about a cycle that there's always at least two units between any two points.
Yeah, that's a good point. Yeah, if I'm at 2 points on a cycle, I could walk clockwise or counterclockwise around that cycle to go from one to the other. That's a great observation. Definitely true. Okay, the backwards direction of this lemma is also going to be well suited for contrapositive. And this is more or less the same thing. I'm just going to be pretty brief about this. So suppose that alpha is, so I'll just say if alpha is not a bridge, that means that when you remove it, the graph is still connected. Right? It does not disconnect the graph. Let's actually give alpha a name here. This is just going to be the set X comma Y again. So if that is not a bridge, then we can still walk from X to Y because the graph is still connected. If the graph is connected, then you can walk from anywhere to anywhere. So in particular, you can still walk from X to Y since G is still connected when alpha is removed. This is alpha. So if we remove that edge, we can still get from X to Y some other way, and that means that alpha is part of a cycle. I'll draw a picture of that in a second. finish this over here maybe. So alpha is part of a cycle. The picture for that would just be, here's alpha right here with the vertices X and Y. And even without alpha, the graph is still connected, so there has to be some other way of getting from X to Y. And whatever that other way is, when you then throw in the edge alpha again, you now complete a cycle. Yeah. So that's the proof of the lemma. And from that proof of that lemma, I can now prove this theorem 11.5.4 in like no time at all. Is everybody good with the lemma though? Nothing too bad here, guys. Really do love combinatorics. I mean, you know, it's nice to not have to rely on so much background. Like this is just kind of, you can play with these results just at face value pretty easily. I'm gonna miss this in a few weeks, I think. Yeah, because next semester I'm going to the other extreme, which is I'm teaching 350, which is where you have to know everything the whole way through. You cannot forget anything along the way because you need every single theorem. And I tell the students to make the flashcards, which are like this tall. I don't care who you take it with. That's just the way that material, it's more about the material.
Yeah,
You know, it's just, you can't let just forget stuff.
that's the class, the first class where I did flashcards.
Yeah, I don't blame you.
Stop scaring us, Dr. Annan.
Let's prove, let's do the proof of theorem 11.5.4. I've already got it stated over there, so I don't think I'm going to state the theorem again. But this one, I'm actually going to prove, this is if and only if as well. If and only if, but you see, I'm actually going to prove the biconditional all together at once. I'm just going to say G is a tree if and only if, right? By definition, every edge is a bridge. Every edge is a bridge. Well, if every edge is a bridge, then that means that every edge is not part of any cycle, right? So by the lemma, put lemma here on this next one, every edge is not part of a cycle. Well, but that just means you don't have any cycles. If you had any cycles, then the edges of that cycle would be part of a cycle, and we're saying no, every edge is not part of a cycle. So this is just, I'm just going to say clear, that basically G has no cycles. Yeah, that's the proof. And it's just really quick. It kind of goes in both directions all at once. Nice. That look okay? The main work is really the lemma, and even the lemma really, to me, isn't that bad. Okay, let's prove the last theorem here, which is the one on the bottom of the board. This is also a nice, pretty chill result. The proof is not that super heavy. I think you'll like it. And then we'll just about going to be done talking about trees here. So let's see. Yeah, so the proof of theorem 11.5.5. So again, I'm just doing the proof now. I won't restate it. The statement is basically over here on my recap for you. And this time we are going to kind of do both directions separately. All right, that's usually what you end up having to do with these things. So I'm going to prove the forward direction here first. Try to get this off a little better. Okay, everybody good? So for this forward direction, I'm gonna assume that G is a tree. We're just gonna do a direct proof. Just go direct on this one. So direct proof, I'm just gonna assume that G is a tree. So what do I have to prove? I have to prove that if I take any two vertices in G, okay, so let's let X and Y be vertices in G. So you just take any two vertices in G. What do I have to do? I have to show that they are joined by a unique path. The assumption that G is connected, which is part of the definition of a tree, guarantees that there is a path between them, right? So we can start off with that. So since G must be connected, this is part of the definition of a tree. There exists a path from X to Y. There's certainly going to exist a path from X to Y. If you turn off your brain and you just imagine, okay, I'm going to start at X and walk until I get to Y, you might start with a walk that's not a path. Remember, a path is not allowed to repeat vertices, but you could take any walk from X to Y, because actually, if you remember what the definition of connected is, it is just that there is a walk from any vertex to any other vertex. But you see, a walk can always be refined to a path, because if you happen to repeat a vertex, then you could, in effect, remove some sort of subwalk of the big long walk so that you're not visiting that vertex more than once. Is that a hand, Teresa?
I was just wondering, is every edge in G is a bridge, so they can't feed the repeated vertex, because if you remove it, then the graph would become disconnected.
Yeah, we could rely on some of these other results to say, yeah, you know, if you had a walk from X to Y that wasn't a path, then that would mean that you actually would be visiting a vertex more than once, and that would involve taking a loop, or some kind of a cycle within the graph. And this is saying, well, no, there are no cycles in that graph. So yeah, we could actually say that this walk was already a path. Okay, but the point is there exists a path. Now, why is it unique? Well, as we always do, to prove uniqueness, you just imagine that there are two of them, right? So if there were two ways to get from X to Y, so if there were two paths from X to Y, of course, they would form a cycle, right? We would form a cycle, and this would be a contradiction. I'll show you a picture here. Again, the picture is not really the proof, but you know, the idea here is if this is X and this is Y, and we have one path over here from X to Y, and then if there was another path from X to Y, then collectively all of those edges would form a cycle, right? So this would be, you know, path number one. And down here, you're kind of imagining what would happen if there was a path number two paths from X to Y. Well, then you create a cycle, and you can see that. It's a contradiction to the theorem that we just got done with, which is the theorem 11.5.4, which tells us that we don't have cycles in trees. Okay, so that's the forward part of the proof. Pretty straightforward. I also have to prove the backwards direction. It's the second part of the proof, so I'll come over here to do this piece of it. And for this piece, we're actually going to use contrapositive. So we did a direct proof for the first part, but now I'm going to go for positive. So that means I'm going to assume that G is not a tree. Assume that G is not a tree at all. Well, one way that it might not be a tree would be if it was not connected. But if it was connected, then you would not have any path between two vertices that are in two different components. So let's just say, so in other words, if we're assuming that G is not a tree, there's several ways that it might not be a tree. One way is that it could be not connected. So if G is not connected, then there exist vertices. Oh, we could say X and Y again. For which there is no path joining them. Okay, and that of course is a contradiction because we are assuming on this backwards direction, we are assuming that every pair of vertices is joined by a path. Okay, so that actually forces the graph to be connected. So the graph is connected, but it's still not a tree. So something else in my list of results over here must go wrong. So let's use theorem 11.5.4 to say that, well, then G would have a cycle. If G is not a tree, but it is connected, then we can say that that we have a cycle. So this means G is connected. So it's connected, but it's not a tree. So by theorem 11.5.4, that was a little bit of writing here, but by that theorem, G contains a cycle. G would have to contain a cycle, and now if I look at that, I think you know what we're going to say. It's kind of what Christian was alluding to a few minutes ago. If you have a cycle in your graph somewhere, and so I don't care where X and Y are, but there will not be a unique path. In fact, there will be two paths from X to Y. I can go clockwise around the cycle or counterclockwise around the cycle, right? So let's just say in this case, if X is not equal to Y on the cycle, take two different points along that cycle somewhere, there are at least two paths. There are at least two paths joining them. And this is also a contradiction, and I'm going to slow down and let everybody catch up with all of this writing. I know it's quite a little bit there. So that's a contradiction because again, we are assuming that there's a unique path between X and Y right here. And Nikolai, what's going on?
We did this. We did.
Uh-huh.
That makes G a tree.
I mean, it would convince me that if you removed one of the edges that was along that path, that it would disconnect that path. But I got this whole big graph that has other edges elsewhere that the path has nothing to do with. And that's where I would have to think about it a little bit more. Yeah, that makes sense. No, I'm glad you're thinking about that though. Yeah, so anyway, that's the rest of that result. Okay, I think I've covered all that. Are there any questions about any of these results? Any of these proofs? These recaps are always really nice. This is like a summary of all of it together in one place. And so as you're thinking about what a tree is, the closer you can get to sort of rattling these off almost, extemporaneously, spontaneously, the better off you're going to be, right? You don't want to be struggling to get these things out. So having them there in one place, I think will help you with that. So, okay. Oh, I wanted to tell you one other concept here, and then we're gonna move on. This is the concept of a spanning tree, which is very important in applications. So, I know you guys don't care about applications, you're all about theory. Uh, If you're anything like me, that'd be the case, so you probably don't care. But I just wanted to tell you what a spanning tree is, and you'll understand why it would be an important application right away. If I just start with a connected graph, so the idea here is start with any connected graph. Actually, I should not make such a joke like that. Turns out that this spanning tree idea is going to be used in a very theoretical way in this next section that we're going to come to right after this. So it's not purely just an application oriented device, but certainly you'll see the application piece of this right away. Let me actually, if you guys don't mind, I'm going to actually draw a graph here to play with. This graph is going to have 8 vertices. I'm going to kind of draw them like so. So I'm going to give you guys a minute to catch up with my drawing here. I'm going to take 2 vertices A and B, and then I'm going to make another edge from B to C. And then I'm going to go from C to D, kind of going around the outside of a figure here. And then I'll move to E. And then I'm going to put F kind of up here in the center a little bit. So that's where F goes, like so. And then F is actually going to connect back to C again. And F is also going to connect to D. Okay. And then I'm also going to connect A to D. Like that. And now I need to add a couple more vertices. I'm going to have a G and an H that are going to be over here a little bit. So, and I'm going to make sure that this whole thing is connected. So A is going to go to H and H is going to go to G as well. Like that. But G also connects directly to A and G connects directly to B as such. I think I've got my whole graph now. Let me just double check my picture here. Yeah, I'm happy with that. Okay, so that is my tree, or my connected graph. It's not a tree, has cycles in it. But what it is you can start removing edges from any connected graph until it becomes a tree. So anything that is not a bridge can be removed. Or in other words, any edge that's part of a cycle could be removed. And there's not a unique way to do this, but you can start removing edges until you get down to a tree. The resulting tree at the end of that process is called a spanning tree for your graph. So let me write this down one by one, and then we'll practice it on this example. Remove any non-bridges to eventually get a tree. Okay, and this is, I just want to reiterate, this is not a unique process. So which non-bridge you remove, or in what order you do the removal will certainly not be dictated. Okay, to eventually get a tree, and then I'm just going to say comma, this is called a spanning tree. It's not the spanning tree, it's a spanning tree. It's because there's more than one. This is called a spanning tree of G. So spanning tree just means that you're reducing the number of edges until you have a tree. And so let's just try it on this example here. I would recommend that when you're taking notes, or if you're trying to take notes on this, because you don't want to just start erasing all the edges or you won't have anything that makes any sense. Keep this graph the way it is, and we can talk down here about which edges we are removing. And I am going to erase them from my picture, but I don't think you need to do the same thing because you're going to have a record of what's been erased right here that you could always reproduce at least. So E, could you please give me an edge that I could remove from this graph to start working on a spanning tree? No, you remove non-bridges. And what that means is that you're going to remove an edge that does not disconnect the graph. Lots of right answers.
BC.
Okay, so if we remove BC, is the graph still connected? Can I still walk from anywhere to anywhere? It looks like it to me, so I could remove BC. So I'll go ahead and write that down here, Jose.
AG.
AG, okay, I'm gonna remove AG. Oh, by the way, before we go any further, how many vertices are in this graph? 8. So the graph has order 8. So how many edges will we be left with by the time we end up with a tree? 7, right? Because that's one of our theorems over there. So as long as we have more than 7 edges, we're not done yet. Okay, so somebody else want to give me an edge that I could remove? Go ahead, Teresa. FD. Okay, FD, I could remove FD right here. Okay, sounds good. Let's see, Julie. AB could be removed. Okay, I'm gonna remove it right there. Remove AB. Kevin, do you want to give me another edge I could remove? FE. All right, I like it. I can still get from F to E, even if that edge is not there. Okay. Kaden, can you give me an edge that I could remove? Okay, if it's taking you more than 10 seconds, let's count how many edges we have left, because maybe we're done. How many edges do we have? 1, 2, 3, 4, 5, 6, 7. I think we're done. Sorry, it was a trick question. Yeah, we're already done here. By the way, counting edges can be a little bit tricky. What would be another way to count the edges if I didn't want to like literally like go through and point at all of them? Julie?
I was thinking like, sort of one shot, like, but I was thinking of removing ED, so it would have been one path, but it still works.
If you remove ED, then
Instead
you
of-
isolate that vertex.
Well, instead of, yeah.
Oh, instead of EF, yes, that's why this is not a unique process. Yeah, there would be more than one way to do it. Is that a hand, Jose?
No, just.
Oh, okay. What I was gonna say is, if you just look at the degrees of the vertices, right? So this is degree 1, this one would be 2, this is 2, this is 2, this is 1, this is 1, this is 3, and this is 2. If you add up all those numbers, 4, 7, 13, 14, right? So the handshaking theorem would then tell you that there's 7 edges, and that's how many you're supposed to have. So you can just always check yourself that way. Okay. Good enough? Okay, awesome. Oh my gosh, the time goes by so fast. They made quite a few of our math classes are now 4 units instead of 3. And so, you know, when I teach for only an hour and 15 minutes, it seems short. Because the 4-unit classes, they meet for like almost 2 hours, right? Yeah, so this semester I don't have that. So the time goes really fast. Yeah, so are there any questions about trees? Anything we've said here? Yeah,
This is just about how it is a spanning tree of trees. So, like, as my for courses, they mentioned like spanning 7 of something.
Of like a vector space.
Yeah, so it literally spans to the entire space. So spanning tree of tree, does that tree span something?
Well, all it really means is that you have enough edges from the original tree to still be able to get from anywhere to anywhere in the graph. It was connected to begin with, right? So the idea is I still want to be able to get from anywhere to anywhere in the graph. And this is sort of a minimal way to keep it all connected up. If you're thinking about like in linear algebra, you can think similarly about what a basis is. It's also a spanning set. And what this means is that any vector in the vector space, and now I feel like I'm back in my other class, any vector in the vector space can be written in terms of your spanning set. You can reach any point of this vector space by starting from the spanning set vectors and doing operations with them. Here I can reach any vertex of this graph from any other point by only using edges that belong to the spanning tree of the graph. Okay, and just like spanning sets are not unique in linear algebra, spanning trees are not unique in graph theory. So there are definitely some nice parallels there. I'm glad that you brought that up. That's a really nice observation for sure. Of course, in linear algebra, you have a lot more going on from an algebraic point of view. Here, we don't have any, we're not doing addition, subtraction, or multiplication, or division, or anything like that. It's just looking at these pictures, which is fun. Okay, I would like, with the 15 minutes or so we have left, I'd like to get started on the next topic, which is really the last topic for our next midterm, which is I want to talk again about planar graphs. So I'm going to jump ahead in the book to chapter 13 for this and talk a little bit more about planar graphs. In my intro video on graph theory that you guys watched a couple of weeks ago, I certainly defined what a planar graph is. It's a graph that, well, let me just recall it for you here. It's a graph that you can draw without having any crossing edges. So changing subjects completely now, right? So a graph, G, is planar. It is planar if it can be drawn if it is possible to draw it, right, so that no edges cross. If we can draw it such that no edges cross. So, you know, for example, here's a graph that, you know, you could draw. Now this is K4. And this is a planar graph because I can redraw it. I can redraw it in an isomorphic manner by simply moving one of these edges maybe on the outside like that. Okay. I will sometimes get students who will say, oh, that's planar, but that's not. No. These are both planar. In fact, they're the same graph. What we would say is that this is a planar representation of the graph. Okay, but both of these pictures are showing me examples of planar graphs. Even if it's drawn with a crossing edge, the issue is, can you redraw it without a crossing edge? And in that case, it would be planar. So K4 is a planar graph. But if you want a nice example of something that's not planar, you can draw K5. So this is K5. And it turns out that this is not planar. Now, to prove that, of course, you have to show that it's impossible to redraw it without any crossing edges. And of course, you can try, like you could try to move some of these edges outside of the central star and put them around the edges of it. But you'll always find that no matter how, you know, wisely you try to do that, that you actually cannot get rid of all of the crossing edges. Now, that is not a proof. Oh, I tried for 3 days to redraw the K5 graph without any crossing edges. I couldn't do it. It must not be possible, right? Actually, it's fairly difficult to prove that this is not planar. It was proved by a mathematician whose name is Kuratowski, if I'm pronouncing that correctly. And later on, I'm going to explain what that theorem says. Essentially, there are two basic kinds of graphs that are not planar, and this is one of them. The other one, incidentally, I might as well show you what it is now. If we do the K33 graph, this is also not planar. Do you remember this is the complete bipartite graph? So this is, I've got two camps. Maybe I'll put the circles up here and the diamonds down here. I've got the two camps, and so the complete bipartite graph has all of the edges that go between the two graphs. And the way I drew it right there, there's a ton of crossing edges, but we could try to, again, move the edges out to the outside a little bit. But again, it turns out to be impossible to do that, to make it so that there's no crossing edges. It turns out that every non-planar graph essentially either has to have a K5 inside of it somewhere or a K33 inside of it somewhere. That's really the only way that you can have a non-planar graph. So that's Kuratowski's theorem, and I'm gonna prove that later. Just wanted to give you a quick heads up that this is not something that can be easily proven. Because you have to prove that you can't do something. And no amount of trying to do it is going to be satisfactory as a proof. Okay, so, but we would like to get some theorems going about planar graphs. That's kind of what I'm hoping to leave you with here. And so I've got a little bit of time to at least get a start on this. So what I'm going to do is I'm going to try to start with a planar graph and prove things that would have to be true about it. So let's do the following. I'm going to assume that G is planar. And what I'm going to do is I'm going to then make a planar representation of it. So we have a planar representation. It's kind of what I was talking about over there. A planar representation of G. And I'm actually going to draw an example over here on the side so that we can talk about this. So let me make a planar representation of a graph. So I'm going to draw it with no crossing edges whatsoever. So you guys can kind of draw this on your own as well if you want, just to kind of follow along with the notes. Then I'm going to make a triangle down out of that, and then I'm going to stick an edge in the middle of there. So this is the graph I want to play with to kind of talk about this for a minute. And what I've drawn there on the board is a planar representation of some graph. So if G is planar, then we've got to be able to draw a picture that's like that. Okay. But the thing that you'll notice about it is that when you have a planar representation of the graph, it actually, not only does it have vertices and edges, but this planar representation also has regions. It creates different regions. Like, so here's a region right here, right? And then there's another region here, and then there's one here. And I'm going to go ahead for the purposes of what I'm going to do, and I'm going to include the outside as well. So there's regions of a planar graph. Like same thing here, we would have, 1, 2, and 3, and 4, right? So you can decompose these planar representations into regions. And what I'm going to say next is something that's going to remind you of the handshaking theorem. You remember how the handshaking theorem works. If you have any edge in the graph, it contributes to the degree of 2 of the vertices that it is incident with. Well, the edges are also kind of forming the boundary of 2 of the regions of your planar representation. So like this edge right here contributes to the boundary of regions 2 and 4, right? This edge right here contributes to the boundary of region 1 and 4. Now, here's an interior edge, and you could say, well, that contributes to the boundary of region 3 twice. It's kind of like what a loop would do in the sense of the handshaking theorem. So let's just make that observation. Each edge of G, each edge of my graph contributes to the boundary, right? It contributes to the boundary of 2 regions in the planar representation. Yeah, so that's kind of making sense, I think. Every edge contributes to the boundary of two regions in the planar representation. And I'll just say here an interior edge, this is a comment I already just made, an interior edge contributes twice to the boundary of just one region. So you might only have one region, and an interior edge would actually count twice to that. Okay, so then I'm gonna make a definition here, okay? And we're gonna hopefully get to a nice little theorem in a minute. Quick definition here, and that is that the number of edges, definition, the number of edges forming the boundary of a region, let me call the region capital R. So if I have one of my regions, the number of edges that forms that boundary is called the degree. We've seen that word before in the context of a vertex, but now I'm using it in the context of a region, is the degree of R, and I will just denote that again as DEG of R. Now, guys, we cannot talk about the degree of regions unless we have a planar representation. So I don't want somebody coming over here and drawing like all these regions in here and talking about their degrees. This is not a planar graph. So this is not a planar representation. So I'm not talking about like these regions, like this, right? That's not what we're talking about. We're saying if we have this planar representation, then we can define the degree of these regions. And then the fact of the matter is that I think comes pretty clearly from this observation over here is that if you add up, if I do a summation of all of the degrees of all of the regions over R. So if I add up the degrees of all of the regions, using the fact that every edge counts towards the boundary of two of its regions, this is just going to be 2 times the number of edges. It's almost the same thing as the handshaking theorem. The handshaking theorem is the same exact thing with degrees of vertices instead of degrees of regions. But it's basically the same thing. So let's just make a little notation here. I'm almost out of time, but I think I have enough time to just look at this particular graph. And I would like to play a quick little game with you here. I would like to know, I'm going to let little r be the number of regions. I'm going to let little n be the number of vertices. And I'm going to let little e be the number of edges. So these are notations, and I'm going to come back next week and be using these same notations again. So just get them down now so we're ready to go with that. In this example, in the pictured example, let's see if you guys can help me out. What is the number of regions? It's just 4, right? And what is the number of vertices? 4, 5, 6, 7, 8, is it? Okay. And then what is the number of edges in that graph? 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It turns out that there is a famous formula relating the R, the N, and the E that is actually always true. And it is called Euler's formula, which actually you've probably heard that in another class. But this is a totally different Euler's formula. This is the graph theory Euler's formula. And here is what the theorem says, guys. It's theorem 13.2.1. It's called Euler's formula. I'm just gonna write it down. We will prove it next week using this fact here. This fact will turn out to be really important, but it is a very simple theorem. It just says, let G be a connected planar graph. Let G be a connected planar graph, then it turns out that this will always be true. If we take the number of regions and we subtract the number of edges, and then we add the number of vertices again. So you alternate plus, minus, plus, you always get 2. You have to always get 2. So you can check it out that it works in this case, and it turns out that it always works. And the way that we're going to prove this, I love it. I love it. We're going to take a spanning tree for our graph. Guys, for a tree, real quick, if I have a tree, I'm probably out of time, aren't I? But I don't care. I'm having too much fun. If I take a tree, how many regions do I have? I would say 1, which is just the outside of the whole thing. Does anybody remember how many edges there are in a tree? N minus 1. So if I take R minus E plus N, that's a 1 minus N minus 1, which is 2 minus N. I add N, I get 2, right? So it's true for a tree, right? So it's true for a tree. So you take your spanning tree and then you just start adding edges into that, and you just make sure that this is continuously preserved. I'll write it all down next week. But that's the idea. That's the idea behind it. All right, guys, have a great rest of your Thursday. Be downstairs if you've got any questions for me. But thank you so much for being here today. I always enjoy it, and I'm looking forward to next time. All right, we'll see you soon.